Let's continue our journey through the wonderful world of carbohydrate metabolism at Sketchyland, where dreams do come true. In this sketch, we'll talk about pyruvate dehydrogenase complex. Recall that during glycolysis, we made 2 pyruvate, 2 ATP, and 2 NADH from 1 glucose. Pyruvate is at the crossroads for several metabolic pathways, but we'll save all the gory details for the Fates of Pyruvate sketch. For the purposes here, pyruvate enters the mitochondrial matrix when oxygen is available. Pyruvate dehydrogenase complex, or PDC, turns pyruvate into acetyl-CoA, which enters the TCA cycle. That's why you see the pyruvates of the Caribbean and TCA right in the background, because pyruvate's dead cove, which represents PDC, serves as a transition point between glycolysis and the TCA cycle. Remember the pirate kid who went on pyruvates of the Caribbean? He's back and eager to ride pyruvate's dead cove. I don't even think he's tall enough to go on it. Anyways, PDC is a 3-complex enzyme that transforms 3-carbon pyruvate into 2-carbon acetyl-CoA. These 3 masts on the ship will help you remember that PDC is a 3-complex enzyme. This step takes place in the mitochondrial matrix, and the pyruvate's dead cove ride sits right on top of a lake that looks ridiculously similar to a mitochondrion. In this oxidative decarboxylation reaction, 1 pyruvate, 1 NAD+, and 1 CoA produce 1 acetyl-CoA, 1 carbon dioxide, and 1 NADH. CoA is short for coenzyme A, which is derived from pantothenic acid. CoA is needed to make acetyl-CoA, fat, cholesterol, acetylcholine, and many more things we won't mention here. You'll see the pirate kid holding an empty CoA cola cup as he approaches the ride. You'll also see him throwing an empty NAD+ drink away. PDC transfers electrons to NAD+ to make NADH, which is used to produce ATP during oxidative phosphorylation. The pirate kid, empty CoA cola, and empty NAD+ drink are located to the left of pyruvate's dead cove to remind you that pyruvate, CoA, and NAD+ are substrates. You'll also see a pirate food stand on the right side. He's selling an NADH energy drink. He's also grilling up some grub, hence the carbon dioxide smoke. And finally, we can't forget that big acetyl cola billboard. These symbols represent the products acetyl-CoA, NADH, and CO2. PDC requires 5 cofactors: 1 TPP from vitamin B1, 2 FAD from vitamin B2, 3 NAD+ from vitamin B3, 4 lipoic acid, and 5 CoA from vitamin B5. These cofactors are represented by a thiaminator fan, an FAD candy bar vending machine, note the wrapper torn off, an empty NAD+ drink, a kid sucking on a lipoic lollipop, and that empty cola cup we talked about before. PDC uses the same cofactors as alpha-ketoglutarate dehydrogenase, which makes succinyl-CoA from alpha-ketoglutarate. Alpha-ketoglutarate dehydrogenase is found in the TCA cycle. 2 enzymes regulate PDC: PD phosphatase and PD kinase. The folks at Sketchyland have created a simple stop-ride switch to control pyruvate's dead cove. The ride shuts down when that shiny red button is pressed. Oh, darn, that rascal kid is up to no good again. He's pulling a P battery from the stop-ride switch, so it doesn't work anymore, and the ride just keeps going on and on and on. This miscreant represents PD phosphatase, which removes a phosphate group from PDC already bound to phosphate to activate PDC. In contrast, kinases kindly use ATP to transfer a phosphate group to a substrate or another enzyme. This kind cast member is trying to fix the stop-ride switch by putting a phosphate battery in it. PD kinase phosphorylates PDC to shut it down. Okay, so what exactly inhibits and activates PDC? The products, i.e. everything on the right side of the arrow, slow down the reaction from making more products. Acetyl-CoA and NADH inhibit PDC by activating PD kinase. If you look closely, you'll see a full acetyl cola bottle and NADH energy drink next to our PD kinase cast member. He's always telling his friends he gets a lot of work done when he's drinking acetyl cola and NADH energy. ATP also shuts down PDC by activating PD kinase. We've placed an ATP battery pack next to our cast member who'll be using a phosphate battery to fix this stop-ride switch. PD kinase transfers a phosphate group from ATP to PDC, therefore shutting down PDC and this ride. High ATP levels mean cells have plenty of fuel and we can slow down ATP synthesis. Therefore, we can slow down glycolysis, the TCA cycle, and of course, PDC. On the flip side, ADP activates PDC. High ADP levels mean cells don't have enough fuel because they've used up most of the ATP. As a result, cells will speed up aerobic metabolism to make more ATP. Okay, let's direct you to another pirate hat-wearing kid who's messing with our cast member. Some would even say he's inhibiting PD kinase. And that's correct. This pirate kid, activates PDC by inhibiting PD kinase. Does he not realize he's making this ride go cuckoo? NAD+ also activates PDC, which makes sense because NADH inhibits PDC. Just like a seesaw, when NAD+ levels are high, NADH levels will be low, and vice versa. Calcium also activates PDC, but the mechanism is different. Exercise stimulates muscle contraction. Calcium levels rise inside cells when muscles are stimulated to activate PDC phosphatase, and therefore activate PDC. We've redrawn the rascal kid holding a calcium ice cream. Calcium ice cream makes this kid do mischievous things, like taking out P batteries from stop ride switches so they don't work. What would happen to PDC if you eat a massive extra-large pizza, all by yourself? It's okay, no one here is judging you. After eating a high-carb meal, blood glucose levels rise and stimulate insulin release to drive glucose into cells. The liver stores some glucose to make glycogen. The remaining glucose will be converted to fat. In order to make fat, we need to make acetyl-CoA first. Eating a lot of food will activate PDC to turn pyruvate into acetyl-CoA, which will be used to make fatty acids. Therefore, eating a large meal activates PDC. Let's redraw these people sitting on the ride eating food to show you that the ride keeps going on while they continue to eat. In contrast, PDC is slowed down by prolonged fasts. Low blood glucose levels stimulate glucagon and favor gluconeogenesis, which makes glucose from non-carbohydrate precursors. Fasting inhibits PDC and makes more pyruvate available for gluconeogenesis. You can check out our gluconeogenesis sketch for more information. All right, let's review what we talked about. Pyruvate dehydrogenase complex, or PDC, serves as the transition step between glycolysis and the TCA cycle. PDC catalyzes the conversion of pyruvate to acetyl-CoA, NADH, and CO2. PDC requires 5 cofactors: TPP, FAD, NAD+, lipoic acid, and CoA. PD phosphatase and PD kinase regulate PDC. PD phosphatase activates PDC by removing a phosphate group from PDC bound to phosphate. PD kinase inhibits PDC by phosphorylation. Acetyl-CoA, NADH, and ATP inhibit PDC by activating PD kinase. Pyruvate and NAD+ activate PDC by inhibiting PD kinase. Calcium activates PDC by activating PD phosphatase. Finally, feeding stimulates PDC and fasting inhibits PDC. Stay tuned for part 2, where we'll talk about PDC deficiency and arsenic poisoning.